Okay, hi. Um, here I'm going to talk about the n-1 integer homology of non-compact manifolds with Ricci FM non-negative. Okay, so first I'm going to talk about the Shen-Sormani theorem. Here it says if n is a complete non-compact manifold and if Ricci is positive, then the n-1 integer homology is 0. And if Ricci is non-negative, then the n-1 integer homology is 0 or z. So we see that the Ricci positive and the Ricci non-negative assumption is geometric, and the conclusion about the homology is topological. And we'll see more theorems like this throughout the talk. And later in the talk, we're going to do a sketch of a proof of this theorem. Okay, so for some historical context, first we have this theorem by Myers. So suppose M is a complete Riemannian manifold with Ricci greater than lambda G, where lambda is positive, then M is compact and the fundamental group is finite. So similar to Shen-Sormani's theorem, we have this geometric assumption of Ricci greater than lambda G, and then we have the topological conclusion, M is compact and the fundamental group is finite. And then we have this theorem by Yau, which says if M is complete non-compact and if Ricci is positive, then the n-1 real homology is 0. And he conjectured that the n-1 integer homology should be 0 as well, which we saw was Shen-Sormani's theorem. Okay, next I'm going to give some definitions that we'll need. So first we have that array is a minimizing geodesic gamma from 0 to infinity to the space, which is parametrized by arc length. In our picture here, all the way on the right, we have the paraboloid, which has this x of t here, which is a ray, because it has that endpoint. So it starts here and then it goes out. And then we have this definition of a line, which says a line is a geodesic from gamma, from negative infinity to infinity, which is minimizing between any 2 points and parametrized by arc length in both directions. So again, in our picture, our first picture of the cylinder, that red thing with 2 arrows is not a line according to this definition, because we see between many points there is a shorter way to get to another point. For example, let's say here, if you can see my pointer, it'd be easier just to go straight like this to get to this point. And then our second picture of the cylinder does depict a line because it is minimizing between any 2 points. Okay, now we have this definition of loops to infinity. So let x of t be a ray, and let h be in pi1 of m at the endpoint x of 0. Let c be a representative of h based at x of 0, basically a loop at the endpoint. Then h doesn't have the loops to infinity property if there exists a compact set K so that every loop which is homotopic to C along X intersects K. So in our picture of the paraboloid here, we have this ray X of T, we have the C of T, which is the representative of H, it's the loop at the endpoint of X of T. And then we have all these, the yellow, orange, red loops are homotopic to C along the ray X, but they intersect the K to, they intersect this compact set K. So in this picture, we have that the H doesn't have the loops to infinity property. Okay, so now we can talk about Sormani's line theorem. It says if M is a complete non-compact manifold which doesn't satisfy the geodesic loops to infinity property, then there is a line in the universal cover. So here in the bottom, we have the M, the manifold, and the X of T the ray, and it lifts to this universal cover, which contains a line. So now we have the Cheeger-Gromel splitting theorem. It says if M is a complete manifold with Ricci non-negative, and if M contains a line, then M splits isometrically as R to the K cross N, where N doesn't contain any lines. So we're going to use the Cheeger-Gromel splitting theorem and Sormani's line theorem to talk about the Shen-Sormani proof. Okay, so now we're going to talk about the easy case of the Shen-Sormani theorem, which is the Ricci positive case. Just to remind you, there were the two cases. If M is complete non-compact with Ricci positive, then the homology is 0. And then if Ricci is non-negative, then it's 0 or Z. So we're doing the Ricci positive case here. So first, if we're going to, in this column, this first column, talk about, we're going to show that M and its universal cover M tilde cannot have any lines. So suppose there exists a line in M and M tilde, then by the Cheeger-Gromel splitting theorem, M and M tilde must split off in R. It must look like R cross N, where R is the real numbers. However, the R part of the R cross N is Ricci flat, meaning like Ricci partial R is 0. So that's a contradiction because we assumed that Ricci was positive everywhere. So that means that M and M tilde must have no lines. Okay, so now by Sormani's line theorem, M has the loops to infinity property. And then by Shen-Sormani and results about it being one-ended, the n-1 integer homology must be 0. So that's the Ricci positive case of the Shen-Sormani theorem. Okay, so now we want to talk about the Ricci non-negative case. And I wanted to talk about the loops to infinity property and how that affects the universal cover, because that is an argument that comes up a lot in the Shen-Sormani proof. So suppose M doesn't have the geodesic loops to infinity property, then by Sormani's line theorem, there exists a line in its universal cover. And then if the space also has non-negative Ricci curvature, well, we have non-negative Ricci curvature and now a line. So by the Cheeger-Gromel splitting theorem, the universal cover splits off in R. It splits as R cross N. So we're going to use this, or this is used a lot in their proof of the Ricci non-negative case. Okay, so now we have enough to give kind of a sketch of the proof of the non-negative case of the Shen-Sormani theorem. So if M is complete, non-compact, and Ricci is non-negative, then we're going to split the cases into the number of n's and the loops to infinity property. So I haven't really given a definition of the number of n's, but I think of it as like a two-ended manifold looks like a cylinder, and a one-ended manifold looks like a paraboloid. So, you know, if you think of it that way, or you can think of it that way. And so if the space has two or more n's, then by the splitting theorem, the n-1 integer homology is 0 or Z. If it's one-ended with the loops to infinity property, then you kind of look at the universal cover. You work there, and then you get that the n-1 integer homology is 0. And then finally, if it's one-ended without the loops to infinity property, then you use sort of the argument from the last slide, and then you get the n-1 integer homology is 0 or Z. Okay, and then finally you get the Shen-Sormani theorem. And just to remind you, it says if M is complete non-compact. And if Ricci is positive, then the n-1 integer homology is 0. And if Ricci is non-negative, then the n-1 integer homology is 0 or z. Okay, so I'm going to change directions to talk about this generalized Ricci tensor, or the M-Bakri-Emry-Ricci tensor. So first, we have the Ricci Fm, which is Ricci plus the Hessian of f minus 1 over m grad f tensor grad f. Here, f is a function from the manifold to the real numbers, and m is a constant that we'll talk more about in the next slide. Number 2 is Ricci xm, which is Ricci plus 1/2 times the Lie derivative minus 1 over m x tensor x. G is a metric, and x is a vector field. So here I have this little chart. So I'm going to start at the bottom where it says most specific, and that's the Ricci tensor. So that's the one that we know most about. That's the Ricci in the Shen-Sermani theorem. And then above that, we have Ricci Fm, which when you plug in a constant for f, then you get the Ricci back. And then finally, we have Ricci xm, which is the most general. And if you plug in grad f for x, then you get Ricci fm. And then, because of this, we can call the Ricci fm gradient M-Bakri-Emry Ricci curvature because of the grad f. And then we call Ricci xm non-gradient Bakri-Emry Ricci M-Bakri-Emry Ricci curvature. Okay, so what is m? So m is that constant. Here, consider Ricci fm is Ricci plus the Hessian of f minus 1 over m grad f tensor grad f equals lambda g, where lambda is a positive constant. So m here is a constant, and the sign of m is important. So here, if m is positive, then the Cheeger-Grommel splitting theorem holds. In fact, the m positive case, you can kind of do the same thing as the Shen-Sermani proof because the splitting theorem holds. If m is infinity or m is less than 1 minus n, then the splitting theorem holds if f is bounded above. So here, the m equals infinity case is basically like if you plug in m equals infinity here, then this term goes away, right? So that's the Ricci-Soliton case. So in this case, the Cheeger-Grommel splitting theorem holds if you add this extra assumption that f is bounded above. If m equals 1 minus n, then there's a warped product splitting theorem, which I will talk about more later, but basically it's not as nice as the Cheeger-Grommel splitting theorem, so there are some problems. And here, this m equals 1 minus n, this means that m is negative, right? Because, or I guess 0, but then finally, if 1 minus n is less than m is less than 0, then we don't know if there is some kind of splitting theorem. And we're going to focus on this 1 minus n case since the splitting theorem doesn't hold. Okay, so what is our biggest issue with proving the Shen-Sermani theorem if Ricci Fm is non-negative and m plus n equals 1? Or the m equals 1 minus n case. So in the Shen-Sermani case, this top case, if Ricci is non-negative and if m contains a line, then by the Cheeger-Grommel splitting theorem, m splits off in r. So m looks like r cross n, where r is the real numbers, and the metric also splits as the metric on r plus the metric on n. So in the Ricci Fm non-negative, where m plus n equals 1 case, if m contains a line, then we have this warped product splitting theorem by Wiley, which says that, yes, the topology splits, the space splits as r cross n, it splits off this r. However, the metric doesn't split as the metric in r plus the metric in n. It splits as the metric in r plus this function, non-negative function squared times the metric in n. So this is the biggest hurdle that we have to deal with. And then once you deal with that, you get this generalization of the Shen-Sermani theorem. So if M is complete and non-compact, and if Ricci Fm is positive for m plus n equals 1, with f bounded above by a constant, then the n minus 1 integer homology is 0. And if Ricci Fm is non-negative for m plus n equals 1, with f bounded above and below, then the integer homology is 0 or z. And here's a remark that this above theorem also holds for Ricci xm non-negative for m positive. So this is the non-negative, non-gradient Bakary-Emery-Ricci curvature for m positive. So this also holds. So before I move on, one question you might have is, I have this extra assumption here that the function has to be bounded above in the first case, and the function has to be bounded above and below in the second case. So you might ask if this is a necessary assumption. And this slide is saying yes. So here, again, this is just copied over from the last slide. If Ricci Fm is positive for m plus n equals 1 with f bounded above, then the n minus 1 integer homology is 0. So consider m equals the sphere of dimension n minus 1 cross R with m equals 1 minus n, and let f be a function from the manifold to the real numbers, and let f of x be r squared, then Ricci Fm is positive, but the n minus 1 integer homology is z and not 0. And we see in this case that the f is clearly not bounded. So this shows that we do need this f bounded above assumption. Okay, now I'm going to talk about this theorem by Fang, Li, and Zhang. It says if M is complete, non-compact, and if Ricci phi infinity is non-negative, and we have this limit condition, then the splitting theorem must hold. So a corollary of this is that if grad phi goes to 0, then the splitting theorem holds, and the n minus 1 integer homology is 0. And then I have this remark that we can give an example where the splitting theorem doesn't hold and grad phi is bounded and the Ricci phi infinity is positive and the n minus 1 integer homology is z. So this example is long, which is why I don't have it listed, but we can give this example. Okay, and now here are the references. And then that's it. So thanks for watching my talk.